Okay, so in the previous video, we considered the cross product of the velocity with the magnetic field, and we found that only 2 out of the 4 paths along a closed loop following the Cartesian coordinates were going to contribute to the overall VEMF. Because the VEMF is this closed loop integral, like all integrals, we should be able to break this into pieces so that we can solve it more easily. Those pieces are the different paths from path 4 to 1, 4 to 3, 3 to 2, and 2 to 1. So we have 4 different paths that we can use to make up that loop. We determined that 2 of those paths would not contribute, so we just need to make integrals for path 1 to 4 and for path 3 to 2. So let's write those integrals now. So we knew that U cross B, we know that that is equal to this, and we can see that the DL is this Z hat DZ. So we're going to have 7.5 mu naught I1 crossed with DZ. And because it's in the Z direction, we need to determine what the limits are going to be. So for path 1 to 4, we should determine some limits. Now, we know that the length of the loop is 20 centimeters, but we aren't given an origin here. So let's just say, let's call this, for convenience, let's say that this is y equals 0. This will make it easier to integrate from y equals 0 up to an upper limit of 20 centimeters. And then for the second integral, we have 7.5 mu naught I1 2 pi y. And then from the DL, we have that this will be dz. So again, we'll need to choose our limits here. And this is for path 3 to 2. So for path 3 to 2, we'll integrate from 0.2 down to 0. So this integral goes from 1 to 4. And this integral is from 3 to 2. So we can solve this now quite simply for both of these cases. And one of the last things that we have left now is determining any unknowns that we have. So let's take a look at our problem again and see if there's anything that we are missing. So mu naught, we know what this is, right? This is a constant, so that's great. What about the current I1? Well, looking at the problem statement, this was also given, so we know what this is. This is a constant, 2 pi, that's a constant. So the only thing that we have is this y. So let's check what we should evaluate y at. What should y be in this? So on the loop, if we go back to here, we can see that we are told that the loop on this edge of the loop is at y naught, which must mean that this edge of the loop is all the way out to y naught plus 0.1 meters. Okay. So we've gone all the way out to 0.1 meters. So let's evaluate these respectively. So this was path 1 to 4, and path 1 to 4 is at y naught. Whereas path 3 to 2 is all the way over here at y naught plus 1. Sorry, y naught plus 0.1 meters. So that gives us, finally, an expression this. If you were to simplify this even more by plugging in your constants, we'll get 3 to the minus 6. For this. And now we can apply Ohm's law. Where VEMF is equal to I2 resistor plus resistor. And if we were to rearrange and solve for this, you will get 150 in nanoamps for the current I2. So I hope this helped you understand a motional EMF problem a bit better. And I did want to point out that I realized I made one small mistake here, which is that I was, in the previous video, I was calling this Y, but clearly we were integrating in the Z-axis from Z equals 0 to Z equals 0.2. So I hope this clarification helps you. Thank you, and I'll see you in the next video. Bye.